Hi everyone. So this video is about a brief discussion of the approximations or the assumptions that we needed to do in order to reach out the analogy that we reached out in the last video, which is basically that the number of time steps needed for early stopping is approximately equal 1 over epsilon alpha, where epsilon is the learning rate and alpha is the L2 is the corresponding regularization coefficient that you should choose for an L2 regularization strategy so that you get the same effect or the same solution as early stopping. So the main enabling approximation is to have a quadratic approximation of the cost in the neighborhood of the unregularized min. Right? So basically that means what? That means that I'm looking at the unregularized cost, at the minimum of that unregularized cost, right? And I'm assuming that the function will look approximately quadratic in the neighborhood of that minimum. Now, this is not actually a very far-fetched assumption, because the function will look, even if it's not quadratic in the neighborhood of the optimal, then it's very likely that it will look convex, right? So remember, even if the function looks like this, and this is the optimal, right? So we are just saying not that the whole function looks quadratic, but in the neighborhood of that optimal, the cost will look quadratic, right? But there is an implicit, stronger assumption than just saying that in this analysis. And the assumption is that our solution, whether we use early stopping or L2 regularization, will actually be in that neighborhood, right? So in that example, it says that so we are assuming that our solution will be in the local neighborhood of the unregularized cost optimal, right? So let's say this is the unregularized cost. So if I end up having early stopping putting me in a region like this, then this whole analysis doesn't really apply, right? So, and that's really the stronger assumption here. So there are some light assumptions, like assuming there is no bias. That's, of course, there will be a bias, and the bias will affect the cost, but we are just saying that we ignore it for this analysis because regularization really works for the parameters, and there are far more parameters than biases. So we are assuming that we are ignoring the effect of the bias on the cost function. Right, because that will be a constant effect. So that effect will be the same whether you apply L2 regularization, and there is an implicit assumption that that within the bias effect in the early stopping will not be very large. So usually the bias is actually, and that's why we don't regularize them for L2. The biases, there are very few of them, and their role is to figure out first order statistics, which are the mean values of the features. So the bias of every hidden layer unit, its role is to estimate some first order statistic function or the expected value of some function, and that's typically something that does happen in the very first few iterations of training. So that's why it's relatively safe to say assume there is no bias in the analysis of early stopping, because it's very unlikely that early stopping will make us stop before the bias values are the right values for learning. So that assumption right here is okay. That assumption itself, quadratic approximation, is not that strong, but what's strong is that the whole analysis is within the neighborhood of W star or omega star, right? So that's a fairly strong assumption, because that assumption relies that we have some optimization strategy, and that we will discuss in detail in the third section. An optimization strategy that enables reaching the neighborhood of omega star, right, or the unregularized minimum, and that optimization strategy will enable that whether we are using early stopping or we are using L2 regularization. So that was the main or the major assumption, the quadratic approximation, and now we are aware of where actually where the risk in that assumption is. It's not that the function looks quadratic around the minimum. That assumption could be reasonable, but it's that we are within the minimum. That's the strong assumption. The other assumption we needed to make right here was that the lambda i's are very small. Right? And remember, this is not an absolute thing as saying that the lambda I in general are very small. No, all we need is that epsilon lambda I is small and lambda I over alpha is small. Meaning that lambda I is small with respect to the inverse of the learning rate. So we are using a small enough learning rate such that lambda I compared to 1 over epsilon is small. And we are using a large enough regularization coefficient for L2 such that lambda I is very small compared to the value of that alpha. Now, what does it reflect, the assumption that lambda I is small? It reflects that we believe that we can perturb W star without changing the cost function by much. So the second derivative in all directions, so we need all the lambda i's, the second derivative in all directions, or the eigenvalue of the Hessian in all directions corresponding to the eigenvectors. These values are small, so basically the first derivative is growing around the minimum slowly, right? So it's not like this, the minimum, we are assuming it looks more like this, it's more flatter. Right? And that is an assumption needed anyway in most regularization strategies because that's the same as saying I can perturb omega star without changing the cost by much, so that regularization will pay off. Otherwise, regularization will result in a significant increase in the training error, right? So if I am here, I perturb by a little bit, the unregularized cost will jump by a lot. Right? So again, since we are using generalization, regularization anyway, whether early stopping or L2, that assumption is also not a very aggressive or far from reality assumption. So it's really the key thing that's enabling this, the key strong assumption. Since the bias assumption is not a very aggressive assumption, since the lambda I assumption being small is not an aggressive assumption, since the quadratic approximation in the neighborhood of omega star is by itself not an aggressive assumption, what is aggressive here is assuming that there is an optimization strategy that will bring us close to the unregularized minimum. If that's not true, and that can be very difficult in some cases, as we will see in the next section, if there is no enabling optimization strategy like this, then this analysis would not really hold. Otherwise, even if not exact, as in the tau equal 1 over epsilon alpha, the proportion relationships in that equation could still hold or are very likely to hold, which is basically that tau is inversely proportional in a linear way to epsilon and alpha, to the learning rate and the L2 regularization coefficient. Thank you.